This will be part 2 of section 5.4, and it's the last features that we need to learn how to find on the graphs of fractions. And problems 33 through 48, the instructions ask me to find a horizontal asymptote. A horizontal asymptote is a line that has an equation y equal to some number that the graph gets attracted to on the far left edge of the graph and the far right edge of the graph that doesn't really control the graph in the middle, kind of close to the origin. So this is just a horizontal line with the equation y equal to some number that the graph gets pulled to as you get to the far left edge and the far right edge of the graph, but not around the origin. There's a strategy for finding the horizontal asymptote, and it is completely dependent on the x term in the numerator that has the highest exponent and the x term in the denominator that has the highest exponent. In problem 34, the x term in the numerator that has the highest exponent is the 6x to the first term, and the x term in the denominator with the highest exponent is the 2x to the first term. There's a little piece of paper that I stole from the internet, or something I copied from the internet, to explain how to find the horizontal asymptote of the graph of a fraction. And it very specifically says when you're looking at a fraction to specifically find the term with the highest exponent in the numerator, find the term with the highest exponent in the denominator, and then compare those exponents. If the exponent in the denominator is bigger than the exponent in the numerator, then the x-axis, or y equals 0, is the horizontal asymptote. If the highest exponent in the numerator is equal to the highest exponent of the x term in the denominator, then the horizontal asymptote is the line y equals, and you divide the numbers in front of the terms with the highest exponent. And if the highest exponent in the numerator is bigger than the highest exponent in the denominator, you don't get a horizontal asymptote, you get a slant asymptote. I might have run through that so quickly that it wouldn't make any sense, and that's okay. I'm going to go through this sheet a bunch of times and you'll get it down. In this particular problem, to find the horizontal asymptote, I look at the term in the numerator with the highest exponent, and that's the 6x to the first power term. I also look at the term in the denominator with the highest exponent. That's the 2x to the first power term. Because the term with the highest exponent in the numerator has the same exponent as the term with the highest exponent in the denominator, then there's going to be a horizontal asymptote, and I divide the coefficients of those x terms to get the horizontal asymptote. So for problem 34, the horizontal asymptote can be gotten by writing y equals, and I'm going to make a fraction, and the coefficient of the x term with the highest exponent is going to go in the numerator, and the coefficient of the x term with the highest exponent from the denominator is going to go in the denominator. That's going to give me y equal to 6 over 2, which reduces to y equal to 3. The answer to problem 34 is going to be y equal to 3, and let me show you graphically what happens for that. I'm going to graph this function, and I'm going to graph the horizontal asymptote of y equal to 3. Unlike with vertical asymptotes, I can enter this without any trickery. So I'm going to enter the function y equals clear parentheses, put the numerator in the parentheses, and put the denominator in a parentheses. I'm going to zoom standard. This is going to be the graph of the function without the horizontal asymptote. And now I'm going to add in the graph of the horizontal asymptote by going y equal to 3 without any multiplying by 1,000, because it's a horizontal line. I don't need to do any trickery. And you'll see that off to the far right edge of the window, the graph starts getting closer to that line. Similarly, off to the far left edge of the window, the graph's going to get closer to that line. If I make the window bigger, meaning make it go further to the right and further to the left, I'll see better the impact of that horizontal asymptote. So if I change my window and maybe change the x's to be minus 30 to positive 30, when I graph it, I'll see more clearly how that horizontal asymptote, how the graph is drawn to that horizontal asymptote. You'll see that eventually the line gets so close to that horizontal asymptote that you can't even distinguish the graph from the horizontal asymptote. So I don't need to graph any of these, but I can. And a horizontal asymptote, in the middle by the origin, the graph doesn't have to be close to that horizontal asymptote. But as I go far off to the right and far off to the left, the graph will get really close to that horizontal asymptote. So you should be able to stumble through problem 33 pretty nicely, hopefully. And I'll go on and do problem 36. And in problem 36, in the numerator, I'm looking at the term with the highest exponent, which is 3x to the first power. In the denominator, I'm looking at only the term with the highest exponent, which is x to the second power. In this case, the highest exponent in the denominator, with the x squared, is bigger than the highest exponent in the numerator, which is the 1. That's this case here. If the highest exponent in the denominator is bigger than the highest exponent in the numerator, or conversely, if the highest exponent in the numerator is less than the highest exponent in the denominator, then there's no algebra to do to find the horizontal asymptote. The horizontal asymptote is the equation y equal to 0. That's what this little saying says here. So when I go to do problem 36, my answer is not going to require any algebra because the bigger exponent is in the denominator. It's just going to be the horizontal asymptote is y equal to 0. And let me graph this to show you that that's the case. I'm going to graph the function parentheses 3x, I think that was a minus 18, I hope it was, maybe it was a plus 18, 3x minus 18 divided by x squared plus 5x plus 6. And I'm just going to go back to a zoom standard. And the x-axis is going to be the horizontal asymptote. So this graph should get really close to the x-axis as we go far to the right and far to the left. Already as I'm even at x equal to 4, the graph is already indistinguishable between the graph and the x-axis on my calculator. If I went a little bit further off to the left by changing my x-min to like maybe negative 20, the graph is going to get really, really close to the x-axis. So when the bigger exponent is in the denominator, there's no algebra to do for the horizontal asymptote, and the horizontal asymptote is the x-axis, which has the equation y equal to 0, and the graph will ultimately get indistinguishably close to indistinguishable from the x-axis, which has the equation y equal to 0. Your problem 35 should work just the same. I'll move on and do problem 38, and you can do 37. To do 37, I look at the highest exponent term in the numerator and the highest exponent term in the denominator. I ignore the rest of the numerator and the rest of the denominator. Because the highest exponent term in the numerator has an exponent of 2, which is equal to the highest exponent term in the denominator, I'm going to find the horizontal asymptote by dividing the numbers in front of those x's. The numbers in front of the x in the numerator I can see as a 3. The number in front of the x in the denominator I can't see, but it's implied 1. The horizontal asymptote, which I'm going to abbreviate HA, is going to be y equal 3 divided by 1. And my answer to problem 38 is the horizontal asymptote is going to be y equal to 3. You should be able to do something similar for 37. I'll move on to 39 and 40. And in 39 and 40, I'm just looking at, in the numerator, the term with the highest power of x, ignoring the rest of the numerator. In the denominator, the term with the highest exponent of x, ignore the rest of the denominator. If the exponent in the numerator is tied with the exponent in the denominator, then the horizontal asymptote you get by just writing y equals, and you make a fraction that has the coefficients of those x terms. And that's all there is to do for problem 40. Similarly, that's all there's going to be to do for 39. But in 39, you have to think of the terms in the numerator and the denominator for the x squared terms of having 1s in front of them. 42 is tricky because the numerator doesn't have an x to the first power term. You can think of the numerator as being 0x plus 2 over x minus 8 if you want to. Or better yet, we can think of the numerator being 2x to the 0 over x minus 8. So there's two different ways to consider the numerator in problem 42 because it doesn't have an x term. You could give it an x term of 0x to the first, and that would simplify to 2 over x minus 8 because 0x is 0, and that would leave me with a 2 if you simplified that. Or you can make it 2x to the 0 over x minus 8 when you think of reimagining the numerator with an x, because x to the 0 is 1. This would mean 2 times 1 over x minus 8, which is 2 over x minus 8. Each one of these would give me the same horizontal asymptote. The top version, I'd have to look at the term in the numerator with the highest exponent, the term in the denominator with the highest exponent, and I've made these have the same highest exponent. The numerator is a 0x to the first, the denominator is a 1x to the first. The horizontal asymptote, when there's a tie between the exponents, is going to be y equals, and you divide the coefficients. In this case, it's going to be y equals 0 over 1, and that simplifies to 0. So looking at problem 42 with the numerator written like this, you get y equals 0 for the horizontal asymptote. Looking at problem 42 with the numerator like this, the highest exponent term in the numerator is 2x to the 0. The highest exponent term in the denominator is x to the 1x to the first. When the highest exponent in the numerator is less than the highest exponent in the denominator, the horizontal asymptote is y equal to 0, and there's no algebra to do. So this way to look at this also gives me a horizontal asymptote of y equal to 0. When there isn't an x term in the numerator, the horizontal asymptote is always going to be y equal to 0, regardless of how you try to rationalize it. So when there's no x in the numerator of a fraction, you don't technically have to do any algebra. You will always get a horizontal asymptote of y equal to 0. So immediately, if I was doing 41, I just glance at that. If I'm asked to find a horizontal asymptote and there isn't an x in the numerator, I can default and say the horizontal asymptote is y equal to 0, or I can consider that fraction 0x plus 6 over x minus 6, or I can consider it 3x to the 0 over x minus 6. Both this one, if you do the algebra that's similar to this, or this one, if you do the non-algebra that's similar to this, will give you the y equal to 0 for the horizontal asymptote. For problems 43 and 44, I look at the terms in the numerator with the highest exponent and the term in the denominator with the highest exponent, and I ignore the rest of the fraction. Because the denominator's exponent is bigger than the numerator's exponent, the numerator's exponent is less than the denominator's exponent, the x-axis, or y equal to 0, is the horizontal asymptote, and there's no work to do. So for 44, the answer is the horizontal asymptote is going to be y equal to 0, and anytime the highest exponent in the denominator is bigger than the highest exponent in the numerator, you get y equal to 0 for the horizontal asymptote. For problem 46, I ignore everything in the denominator and the numerator that isn't the highest exponent. The highest exponent term in the numerator is the 3x, which is really 3x to the first. In the denominator, the highest exponent term is x squared. The highest exponent in the numerator is less than the highest exponent in the denominator. There's no algebra to do to get the horizontal asymptote. It's just going to have the equation y equal to 0. My answer to 46 is the horizontal asymptote is going to be y equal to 0. Same deal for 48. I kind of overkilled these. Let me do your 47 because it's different. For 47, your term with the highest exponent in the numerator is the 5x squared. Your term with the highest exponent in the denominator is the x squared, which is really 1x squared. When there's a tie between the numerator and the denominator, you divide the coefficients of that term to get the horizontal asymptote. So in 47, the horizontal asymptote is going to have an equation y equal to 5 over 1, and that fraction reduces to y equal to 5. So that would be the answer for number 47. So the last few problems in our section want us to find an equation of a slant asymptote. You get slant asymptotes when the highest exponent in the numerator, in this case 2, is bigger than the highest exponent in the denominator. There's only one x term in the denominator. It has an implied exponent of 1. And anytime the higher exponent in the numerator is bigger, the highest exponent in the numerator is bigger than the highest exponent in the denominator, that's when you get a slant asymptote. And if there's only a separation of 1 between the highest exponent in the numerator and the highest exponent in the denominator, then the slant asymptote is a line, and that's the only kind of slant asymptotes we're going to cover. Initially, I had more problems in this section, and maybe they were a little bit harder than they needed to be. So I'm redoing these few problems, made a few friendly problems, and then one not so friendly problem to finish up the section. I'll pull out my calculator when I get done doing my problem, then I'll let you do your problem. So in order to find a slant asymptote for an equation that's a fraction, when the numerator has a higher the highest exponent in the numerator is higher than the highest exponent in the denominator, you're technically supposed to do long division. You're supposed to take the denominator of the fraction and divide it into the numerator of the fraction. The first four problems, 49, 50, 51, and 52, the denominator is very special in that it either has x plus or minus a number, and there's not a number in front of the x. When you have this kind of division problem, synthetic division will give you the same answer as long division. So for problems 49, 50, 51, and 52, there's no number, or there's an implied 1 in front of the x. And that way, for those problems, I can use synthetic division. It will give the same answer as long division. And it's a heck of a lot easier, and it's something that we already know how to do. So on the very last problems, 53 and 54, I'll actually do long division, but you won't be responsible for it on the test. So I'm going to find the slant asymptote for problem 50. Technically, I'm doing this long division, but I'm going to do it synthetic division style. I'm going to write a horizontal line and make this backwards L. And in my backwards L, I need to change the sign of the number in the denominator. So my denominator has a positive 1. I'm going to change that to a negative 1. And up above this, kind of a space above my horizontal line, I'm going to pull off the coefficients from my numerator. The number in front of the x squared is an implied 1. The number in front of the 6x is a 6, and the constant is negative 7. I'm going to do my synthetic division. May have gotten completely rusty on synthetic division, but I think it comes back pretty quickly. To do synthetic division, the first thing I do is I bring down whatever number I have written first. When you do your problem 49, you're going to bring down a 1 as well. So I brought down my 1. And then the rest of the work for synthetic division is to multiply and then combine, add or subtract. Add if the numbers have the same signs, subtract if they have opposite signs. So now I'm going to multiply this negative 1 times that 1. I get negative 1. I write it under the 6. If these numbers had the same signs, I would add the numbers, but because they have opposite signs, I subtract them, and 6 minus 1 is 5. And then I'm going to go this negative 1 times that 5. Negative 1 times 5 is negative 5. Most of the times we've done synthetic division in the past, we've gotten 0 remainders. We won't get 0 remainders for this section. The numbers I have in the far right-hand column are about to give me my remainder. They have the same sign, so I add the number and keep them negative. The answer to this division, or this long division problem that I simplified by synthetic division, would be found by taking this 1 and putting an x next to it 1 power lower than the x in the numerator. In this case, that's going to be an x to the first power. So this 1 is going to have an x to the first next to it. I need a sign between the 1x and the 5, and because there's no sign, I'm going to put a plus sign in there. The second number is going to be my constant, and then the last number is my remainder. The equation of the slant asymptote, this is the right side of the equation, and generally, because I'm finding an equation of lines, I'm going to throw a y equals to it. So the answer to find the equation of the slant asymptote for this problem is going to be y equal to x plus 5. I'm not going to show the remainder. And that's all I need to do. I don't need to graph this, but let me graph this to show you that this will work just fine. This might be a new calculator. This is newish for me. I don't remember if I had it when I did the video previously. So I'm going to enter this fraction by putting into y1, just the fraction. Well, if I could actually do that. Just the fraction. Numerator goes into parentheses. Denominator goes into parentheses. So that's the function itself. I'm going to just do a zoom standard to see what this looks like in terms of a graph. If I could actually get it out of the glare. Do a zoom standard. I don't think this window is going to be appropriate. I don't think I'm going to see much of the graph here. And to see better how the slant asymptote works, I'm going to blow this window way up in terms of the y's. I'm going to make the y's go really high, maybe negative 50 to 50. I don't know if that's going to be high enough. Yeah. Seems reasonable. Now let me put this slant asymptote onto this graph and show you how the graph and the slant asymptote work together. So into my y equals, I'm going to put my slant asymptote into y2. This y equals x plus 5. Don't have to graph any of these, but this will give you an idea if your equation is right. When I hit graph now, look how close the graph and that line attach to each other. If I made my window get bigger in terms of the x's, maybe make my x's go from negative 20 to 20, eventually you're not even going to be able to see the graph and the line that I'm drawing will look exactly the same. So this line, this slant asymptote, it tracks the graph so closely that you almost can't see that there's two different graphs, the graph of the original function and the graph of the slant asymptote. So done with that, that's probably all the graphing I'm going to do. Let me help you through problem 49 so you can get one done for free. If I was doing problem 49 and I wanted to find the equation of the slant asymptote, I take the denominator. Since it just has an x plus a number, I can do, instead of long division, synthetic division, change the sign of the 3 to negative 3, take the numerator and put it kind of above the solid line that I drew, and the numbers from the numerator that I need are the 1 that's implied in front of the x squared, the 5 that's in front of the x, and the negative 6. I would bring down the 1, multiply the negative 3 times 1 to get negative 3. If the numbers have the same signs, you add. If they have opposite signs, you subtract. So 5 minus 3 is 2. And then negative 3 times positive 2 is negative 6. If the numbers have opposite signs, you subtract. If the numbers have the same signs, you add. So the result of my synthetic division is going to be 1x. I get that 1, and I get an x with 1 degree less than the numerator that I did the synthetic division with, so I get an x to the first power. Need a sign between these two. Since there isn't a negative, I'm going to put a positive. I don't get an x there because I'm out of x terms. I would get an x to the 0, which is 1. And then the last term is always the remainder. The slant asymptote, which I'm going to abbreviate SA, is going to have the equation y equal to x plus 2 for your problem 49. Alright, so I'll throw 51 and 52 up on the screen right now. Hopefully you can do 51. I'll do 52. So I'm going to find the equation of the slant asymptote. Because the denominator is just x minus a number and there's not a number in front of the x, to find the equation of the slant asymptote, I can do synthetic division. I change the sign of the number in the denominator, write a horizontal bar, take the numbers from the numerator, write them in order, the 1 in front of the x squared that's implied but not written, the 9 and the 18, bring down the 1, multiply 2 times 1 is 2, These numbers have the same signs, so I add the 9 and 2 and get 11. And then 2 times 11 is 22. Numbers have the same signs, so I add them. 22 plus 18 is 40. The result of my synthetic division is going to be 1x plus 11, remainder of 40. The answer to number 50, the slant asymptote, is going to have the equation y equals x plus 11. Don't need to include the remainder in the slant asymptote. So your problem 51 should work exactly the same. You're going to do synthetic division because the denominator doesn't have a number in front of the x, just x minus a number. You'll change the sign from -2 to +2. Above the slant asymptote, above the synthetic division bar, you'd put a 1, 7, and 10. Bring your 1 down, multiply 2 times 1, add, multiply 2 times 9, 2 times 9, add, and then you're going to get 1x plus 9, remainder of 28. Your slant asymptote is going to have an equation of y equals to x plus 9. If I ever put a slant asymptote on a test, this would be the kind of slant asymptote that I would gift you. The next two and the last two problems in this section, I can't really do synthetic division because of the number in front of the x in the denominator. And the unfortunate reality for 53 and 54, to find the slant asymptote, I have to physically do long division. I'm going to do 53 for you. I won't do 54. I'll never make you do long division on a test. So if you don't want to watch this, skip this problem. It's not going to hurt my feelings at all. But long division is a way to get any slant asymptote. I just made the first few problems friendly so that we didn't have to remember long division. But you might find an evil teacher at some point in the future that wants you to remember how to do long division, but I'm not going to require it. So the proper way to find any slant asymptote is to do long division, the denominator divided into the numerator. And when I do long division, I look at the numbers that are written first, this 2x and this 6x squared, and I ask myself, what times 2x is 6x squared? Well, I know 2 times 3 is 6, and x times x is x squared. So 2x times 3x is 6x squared, specifically because 3 times 2 is 6, and because x times x is x squared, 3x times 2x is 6x squared. So on top of my division bar, I'm going to put a 3x. And I'm going to multiply 3x times 2x. I multiply the 3 and the 2 and get 6. I multiply the x and the x and get x squared. Then I multiply 3x times minus 1. I multiply 3 times minus 1 and get minus 3, and I leave the x. When we do long division, we need to subtract what we put under the initial numerator. So I'm going to subtract 6x squared, and I'm going to subtract the negative 3x. Here I have a double negative, and so this double negative we usually just change to plus. So 6x squared minus 6x squared, they cancel. 5x plus 3x is 8x. I'm going to bring down the plus 3. Now I ask myself, what times 2x equals to 8x? And that's the next thing that's going to go on my top of my division bar. Well, I know that 2 times 4 is 8. I don't need to add an x because to turn 2x into an 8x, it already has an 8. So I just need to multiply 2x by 4 to equal 8x. I'll put the plus 4 on top of my division bar. I'm going to go now 2x times 4. I'll multiply the 4 and 2 and get 8x. And then I'll multiply 4 times minus 1 and get minus 4. Now I need to subtract. The second subtraction produced a double negative, and double negatives I turn into pluses. Here the subtraction 8x minus 8x, the 8x's cancel. 3 plus 4 is 7. This is my remainder. And when we go to find slant asymptotes, the result of the long division or synthetic division, if you can do it, without the remainder is the slant asymptote. So my answer for problem 53, the slant asymptote, is going to have the equation y equals 3x plus 4. If I wanted to, I could graph this, but I'm not really feeling the urge to do this. I don't think I've made a mistake, so I won't. We'll just stop the video here. Slant asymptotes come up again in the next section when we do some graphing as well. So they're got to deal with them, but not this kind. The slant asymptotes with synthetic division come up in the next section. These long division ones don't.